So hello everyone, my name is Johan Ruuskanen and I will be presenting our paper named Improving the Mean Field Fluid Model of Processor Sharing Queuing Networks. So first, some background. Software applications often include multiple stages that requests need to pass in order to finish being processed. Each of these stages, the request will need to share the available finite resources with other requests, and this behavior can be modeled as a queue. A common methodology is then to model the request processing in an entire application using a network of queues that we connect in some manner. So it's always possible to evaluate the queue length PMF using Monte Carlo simulations, but this is expensive, especially when considering certain real-time applications for large-scale cloud applications such as online decision for scheduling and scaling. Instead, it's common to approximate important metrics using different methods such as the fluid model. Other methods also exist for this, but we focus on the fluid model since it gives us both transient solutions and it reduces to a set of ODEs, which are very quick to evaluate given modern methods. So before continuing, we need to define what a mixed network is. So for queuing networks, there exists a plethora of different extensions to model more advanced behaviors and dependencies. One such is to allow each queue to have multiple classes, where each class has its own service time distribution and routing destination. And then we can introduce this transition probability matrix P here, which just defines the probability that a completed request from one class gets routed into another class. And then this routing between different classes, they form paths through the network, and it's possible to partition these paths into chains, such that requests from one chain cannot enter another chain. And if a chain contains classes that allows departures and arrivals, then it's known as open. And if it does not, it's known as closed. So network is simply a queue network containing both open and closed chains. You can see an example here with three queues, in where we have an open chain here and a closed chain here. So for certain types of queue networks, it's possible to derive a fluid model via the mean field approximation. Most notably, if the queue network is translatable to a continuous time Markov chain. And what the mean field approximation tries to do is to approximate this mean queue length here with some x, which is determined by the solution to this nonlinear ODE here. And f is just the drift function of the continuous time Markov chain. And that is just the sum of all possible transitions times their population-dependent transition rate functions. And in certain cases, this converges as a notion known as system size, converges to infinity, and this system size is problem-specific. And quite recently, it was shown that for closed multi-class networks of processor sharing and in queues, which are common when modeling cloud applications, where each class has a phase type distributed service time distribution, then this Kerp's theorem is fulfilled. So a phase type distribution, that is simply just a way of modeling a general distribution by time to absorption in a Markov chain of some transient states. And you can parameterize that by these following three matrices. More about this you can find in the paper. So our contribution with this paper is threefold. First, we introduce a compact mean field fluid model for mixed networks that builds upon the presented previous ideas. Then we also introduce a smooth mean field model for increased accuracy at low system sizes. And finally, we also introduce a closed form approximation of the response time CDF that can be obtained over almost any subset of classes in the network. So for the first part then, the mean field fluid model can be extended to mixed networks by adding transition rate functions for both arrivals and departures to this L set. And it can be shown that the resulting queue length then converges to the solution of this nonlinear ODE when the arrival rates, the servers per queue, and the initial population all goes to infinity. And then for each queue class and phase, we can then write out the resulting drift as a following cumbersome expression. X here is now the population of all phase states in the entire queue network. And this then is just a combination of all of the different phase type, the parameterization matrices and thetas, which are the effect of the PSQ disciplines. And theta is defined as the following, as shown here, where G here is the processor share. The drift function per phase state is a bit cumbersome to reason about. And instead, it can be obtained by stacking the phase type matrices into block diagonals and combining them with P that has been created by enforcing the same ordering. Then we can create this W as follows, and then the drift simply reduces to this. And quite nicely, it becomes a product between a linear face-to-face transition matrix W and a nonlinear effect of the Q disciplines, this theta here. In the paper, we also present some nice properties on W, but we will not go into more details about that here. So for the second part then, it's well known that the mean field model can give a low accuracy for small system sizes. And the error rises as shown here, that the derivative of the mean becomes the mean of the drift, but that's not the same as the drift of the mean. And in fact, it can be shown that this drift of the mean is actually a first order approximation to the mean of the drift. And for the Q network case, this gives that that the mean of theta is not the same as theta of the mean. So natural question then arises: can we find another theta here or theta hat such that this similarity improves? So in mean field theory, there exist methods to do this in general case, by including, for example, higher order moments, but methods such as this introduces new states, which can lead to minor state space explosions when looking at large scale systems. So here we have illustrated the problem a bit closer. So the problem lies in that the mean field approximation does not account for the fact that the stochastic process of the Q length can be on the opposite side of the minimum as captured here in the mean of theta. And this probability of this occurring should be larger the closer to K you are. And the idea then that we got is that we can maybe account for this uncertainty by smoothing this minimum instead. So to do this, we first let theta hat be the following. And then we know that the processor share is identical for all phases in the same Q. We can then sum over all phases and classes in theta I here, and then put these two equal to one another to form a necessary condition. And we then get that the G can be expressed in the following way, where we can recognize this top thing here as the utilization. Unfortunately, this is dependent on the PMF of X, so we need G here to change in some manner, and that we will do by introducing a smoothing parameter. Okay, so one possible function is to use the inverse p-norm, as shown here. And it can be seen as the p-norm of the two sides of the minimum in the processor sharing function. So if we want to, if we use a mean field model with this G hat instead of the nominal G, then we will get an improved accuracy without introducing any new states. And we chose this p-norm since it gives some nice properties. So first, there exists a smoothing parameter such that the necessary condition holds. Secondly, if we let p go to infinity, we will get back the nominal mean field model. And also this G is monotonic in both the sum of X and the parameter p. This means that if we have data from a stationary system, then we can always find this optimal p in log n steps using the bisection search. And also, if we choose a p that is smaller or larger than the optimal p here, then we will always get a better approximation to the necessary condition than the standard mean field model. So for our third and final part then, so response time percentiles are often of interest to obtain in different applications. And for mean field food model, it is possible to via extended state simulation or the Markov inequality to obtain these. But we instead show that we can also do this via a closed form approximation. And so the main idea lies in that the Chapman-Kolmogorov equation gives us that the probability of finding a request a certain state evolves as follows. However, it's a problem that X here is a stochastic variable, so the pi here becomes quite cumbersome to evaluate. So instead, then we can introduce the assumption that every request receives the mean processor share. which then reduces this to a linear ODE, which has the following closed form solution. And then the probability of remaining in this state, then that's simply the complement of the probability of leaving before t. Hence, the response time distribution, or its CDF, can be expressed as the following equation here. This is then possible to extend to cover almost any subset of classes, which we denote CR here. And the caveat is that this subset cannot contain any complete closed chains. Otherwise, there will be some requests which would never depart the subset. It would thus have an infinite response time. And via this CR, we can introduce some parameters here, which we can then use to form an approximation here for the response time CDF. And it can also be shown that this CDF is a valid CDF for all valid choices of CR and matrices. And this approximation is better the less stochastic the Q system is, which unfortunately means that our closed form approximation here is worse the closer to overloading we are, due to the assumption that each request receives the mean processor share. So we then performed a larger simulation experiment in order to test how accurate the smooth mean field fluid model was, and also how robust a fitted P is to system perturbations, and how good the response time approximation is. And to do this, we considered the following two-tier model, as can be seen here, and where we have both clients and external users using this application, which consists of a front end and a back end. The front and the back end services are both modeled as PSQs, while the client is modeled as an infinite queue, and the external users are modeled as external arrivals. And this then can be translated into a mixed PS network with the two following chains, one open and one closed. And you can find more detail about how this is set up in the paper. So what we then did is that we simulated the system to fit P here on some nominal data. And then we wanted to see how well it was able to predict the system metrics after performing some random perturbations on both the workload, the horizontal and vertical scaling of this system. We then drew 1,500 of these random perturbations and calculated relative errors over different important metrics. And you can see three of them here in these histograms, where the first one had the mean relative error over the class populations. And here we have the mean relative error over the 95th percentiles. And here the mean relative error over the 95th percentiles in CR. And CR here is simply the closed chain without the client queue. And the blue one here is the mean field model. And the red one here is a smooth mean field model where we have refitted P for every perturbation. And the green one here is the smooth model where P is the one we fitted to the baseline system. And from it, we can deduce mainly three things. Well, first, the smooth mean field model seems to outperform the standard one by quite some margin. And secondly, using the P fitted from the baseline system does not seem to alter the result that much, which seems to suggest some robustness around the nominal system. And then lastly, the response time approximation seems to yield a quite accurate result. So in the paper, we also have some more smaller examples for each contribution part in detail, which you can see there. And yeah, if you're interested in looking at this code, you can find it on GitHub here. In conclusion then, we have introduced a compact mean field fluid model for mixed networks. We also introduced a smooth mean field model for increasing accuracy at low system sizes that is computationally cheap even at very large scales compared to other more general approaches. I've also introduced a closed form approximation of the response time CDF that can be obtained over almost any subset of classes in the network. Thank you for listening.